lab we did in physics was about the motion of a falling object. So, free fall. In order to discuss free fall, we have to discuss two forces, the gravitational and the drag force. As you can see on the top left of this slide, the weight is given by the mass times gravity, and the resistance depends on the square of, so drag force, depends on the square of the velocity. A free-falling object is an object that is falling under the sole influence of gravity, and an object that is falling through the atmosphere, as I said before, is subject to the gravitational and drag force. They're in opposite directions, and so one of them would be considered in the negative direction depending on the axis you choose. The second force, so the drag force, is the aerodynamic drag of the object. It's a result of collisions of the object surface with air molecules, and the two factors that affect the drag is the speed, as mentioned before, and the cross-sectional area of the object that is falling. If we go to Newton's second law, the momentum principle, F equals mass times acceleration. Acceleration on Earth is 9.81 meters per second squared. The net external force is equal to the difference between the weight and the drag forces. So force equals weight minus drag, depending on what axes you choose to be negative. Since they're in opposite directions, one of them is going to have a negative sign. Then acceleration of the object becomes weight minus the drag force divided by the mass. Free fall graphs of a dropped object are discussed on the left bottom of this slide. A position versus time graph for a free falling object can be seen that velocity is increasing in the negative direction and the slope is negative and increasing. A velocity versus time graph for a free falling object, velocity increases in the negative direction and it increases at constant rate. So the slope is negative and constant. The test subject I used for my experiment was a green apple. So now let me get on to the experiment and the results. As you can see on this observed position versus time graph, the apple falls from rest and moves in the negative y direction. Velocity increases in the negative direction as the slope is negative and also increasing. The slope is not linear, which is what we were looking for, because a curved line shows a change in velocity, which is the acceleration. Coding with drag and without drag. If we were to code this with drag, we would see that we need to incorporate both forces. So the force of drag and the force of weight. We have to add both of them in order to get the net force. And the drag is calculated by the equation given on the second line of the code. Below the coding with drag, we have coding without drag, which is basically the weight, which gives us the net force because there's no other force acting on the apple. These are the two different graphs that we obtain for position versus time with different forces. On the left, we have drag with drag, and on the right, we have without drag. As you can see, the object that is without drag has been in the air for a longer time than the object that has drag incorporated into its calculations, which is exactly what we see in this graph right here. As you can see that because we had more data points for with drag, if you just extrapolate the line that says without drag, you can see that without drag is a little bit higher than the object with drag, which means that without drag, the object is going to be in the air longer than the object that has drag. So with drag, without drag, and our observed, as you can see, our observed apple's projectile is way more closer than what we have with drag and not without drag, because in the real life, there is definitely air resistance working on the object as well as the force of gravity. So questioning our data and models. Which model predicts terminal velocity? So terminal velocity is the constant speed that a freely falling object will reach when the net force is zero, which means when the force is balanced out. In order to predict terminal velocity, there would have to be a linear slope since both of the forces have balanced out. The graph that includes the drag and the force of gravity will continue to get more linear over time since drag force will eventually balance the weight force. This will result in zero net force and so terminal velocity. For the graph that includes that is the one you can see right here, the observed and the one in blue. So what if? The only way two objects with different masses will have the same terminal velocity is if they were in a constant and uniform gravitational field. So air resistance affects terminal velocity because terminal velocity is reached when the drag force due to moving through air is equal but opposite to the gravitational force. The time for it to reach terminal velocity if we throw the object will be more than the time it requires to reach terminal velocity if we don't throw the object. And one important thing to note is if one object is shaped like a bullet and one is shaped like a big hollow ball, the big ball will have the same amount of drag at low speeds that the bullet does at high speeds, so the ball's terminal velocity will be a lot lower, meaning that heavy objects will have a higher terminal velocity than light objects.